Okay, so today we're going to go through a quick example of how SwiftComp on the cdmHUB can be used to determine the residual stresses in the fiber and matrix of a fiber matrix composite that has undergone curing stresses from, say, an example temperature change of about 100 degrees Celsius after it's cured and cooled back down to room temperature. So we'll do that by first accessing SwiftComp, and you can do that by going to cdmhub.org/tools/SC standard. This will open a SwiftComp for gmsh instance, and the first thing we have to do is save the file we're going to be working in as something other than untitled.geo. If we leave it as untitled.geo, gmsh will have some issues, and we're just going to avoid that right off the bat. The next thing we're going to do is do the data entry for our material properties. In this example, we're going to use the fiber and matrix properties from the Micromechanics Simulation Challenge Problem 1. These properties are where the matrix is approximately isotropic, but we're doing the data entry the same way that the properties are given as an orthotropic material. And the fiber is approximately transversely isotropic. But again, we're going to do the data entry exactly as it's given in the challenge, so that we don't introduce any errors if we then wanted to try and compare to those results. Just let me check this data entry real quick. All right, that is entering the matrix properties. Next, we will do the fiber. And as I said, the fiber is approximately transversely isotropic. And let me just make sure this data entry was good. All right. So with our fiber and matrix materials added, we can then go on to creating the geometry by clicking the geometry, common structure genome, 2D structure genome, and then other 2D structure genomes. This will allow us to choose either square packed or hex packed microstructure. For this example, we'll do a hexagonal packed microstructure with 60% volume fraction, and we'll choose our constituent materials and add it to the model. Next, we need to mesh our model, and so we'll go to generate 2D mesh and just hit generate. While it's a relatively coarse mesh, we'll accept it for now as we're just doing an example. If we wanted to, we could do a more refined mesh and potentially get better results, or at least converged results. And the first thing we're going to do with this is perform a homogenization step, and we're going to homogenize to the thermoelastic properties. This will open up the resulting document, and from here we can copy out the effective stiffness matrix and the effective compliance matrix and the effective thermal expansion coefficients. I've already done that in this Excel spreadsheet. Just making sure, yes, they are from the same thing. And now using these values, we're going to determine some macroscopically applied strains that we're going to then use in a dehomogenization step. So given the stiffness matrix and the effective CTEs, and notice that I have set a lot of terms equal to 0 that we would expect to be 0, but are not necessarily 0 from the results, but are a significant order of magnitude lower than the primary results. This generally indicates that these terms should be ignored, but if we really wanted to get a correct answer, we should converge the mesh more, and these refine the mesh more to a converged mesh, and these results should get even smaller indicating even further that they are negligible. So we have entered in the effective stiffness and the effective CTE. Now, assuming that we generate curing stresses over just about 100 degrees temperature change, we then have an applied delta T of negative 100. Multiplying that times our CTEs, we have a strain that we can apply to our model in SwiftComp. However, in the SwiftComp for gmsh GUI, we are unable to apply the temperature change directly, so we're no longer applying a so-called eigenstrain, a strain that does not result in a macroscopically zero stress level. We're applying a total strain. So therefore, to get the actual constituent strains, what we'll have to do is multiply, or we will apply these applied strains we determined, simply negative 100 times the CTEs, to our model, get those stress results, then subtract off the appropriate stresses so that the final model would have an average stress state of 0. And we've calculated what those stresses would be here. So, to do a dehomogenization step, first we have to repeat the homogenization, but this time only elastic so that we can store the inverse functions required for the dehomogenization step. And we already have seen those results, so we'll go ahead and close that. Then we go to the dehomogenization option, solid model, and insert in what I've stated as our applied total strains. Now, the top row on this dialog box would be for global displacements from a global type model that we could be driving this micromechanical simulation from. And then this 3x3 matrix C is the direction cosines that would represent kind of global rotations in a global model. But in this case, again, we're not doing this, we're using it just for simple analysis. So these are the strains that we are applying that would simulate a thermal strain. And since we're applying them as total strains, they will cause a resulting stress level that on average is not 0, but using our homogenized properties, we can determine what values of stress we need to subtract away so that our model would be at a stress level of 0. So we will save this and run it. This should open up our homogenized results, and with the most important result being the sigma 1,1 term. So here you see that it says that we have stress in the fiber that is about negative 72 megapascals, and stress in the matrix that is not necessarily homogeneous, and that is another indicator that we need to refine our mesh. We see very sharp changes in stress level, indicating we do not have a converged mesh, that it's somewhere around negative 60 megapascals. So from our, just to scale these legend values, we can add or subtract the negative 67 megapascals that we calculated earlier to get the actual stresses. Right now, the stresses being reported in this analysis are this stiffness matrix times total stress. Now times total strain. But the stresses actually, if this were applied thermal stresses, would be stiffness times total applied strain minus thermal strain, because again, thermal strains should be eigenstrains, therefore not causing any stresses except through incompatibility, which is what the CTE mismatch between the thermal stress, the fiber and matrix cause. They cause incompatibility stresses. So now, taking these, subtracting away the correct stress shows us that if this were a thermal analysis, our thermal strains, our legend here should state negative 4.71 E plus 6, 2.89 E plus 6, and 1.04 E plus 7. So that would mean that our fiber is in compression of about negative 5 megapascals, where our matrix is in tension anywhere from about 3 megapascals to 10 megapascals. And that those stresses could be significant if, say, you were developing a model for the failure at the constituent level rather than at the composite level, as the SciWu failure is. If, say, you were creating a model where you considered the fiber and matrix individually as well as potentially how they homogenize, then it would be important to note that stresses exist in the fiber and in the matrix without any applied load, simply because they were cured at elevated temperatures, at which point the modulus formed, then cooled down, and the constituents having different coefficients of thermal expansions, specifically the fiber having a very small one, if not negative, the matrix having a relatively large one, ends up attempting to contract the matrix more than the fiber would contract, therefore putting the matrix into tension and the fiber into compression. All right, that is it for this video. Thanks for watching.